This is my quiz corrections for acid-base quiz 1B, and I'll be going over all the problems in this quiz that I missed points on. The problem is lactic acid is a monoprotic acid that dissociates in aqueous solution as represented by HC3H5O3 aqueous yields to H plus aqueous plus C3H5O3 minus aqueous. Lactic acid is 1.66% dissociated in 0.5 molarity HC3H5O3 aqueous at 298 Kelvin. So for part A, we have to write an expression for acid dissociation constant Ka for lactic acid and calculate its value. On the quiz, I got that right, and so the equilibrium equation is K is equal to the concentration H plus times concentration in C3H5O3 minus divided by the concentration of HC3H5O3. And then after that, I kind of got confused with Ka, or how to calculate Ka. So what we're supposed to do is take the 0.5 molarity and multiply it by the 0.0166, because that is the percent dissociated in the 0.5 molarity, and we get a 0.0083 molarity for our X value. From there, we're going to set up an icebox using the equation provided to us before. So we have 0.5 molarity of HC3H5O3 aqueous and none of the initial concentration for H plus and C3H5O3 minus. And we use the coefficients from the equation to figure out the change was minus x plus x and plus x. And we also can solve from equilibrium for that. So for HC3H5O3, its equilibrium is 0.5 minus x, and for H plus as well as C3H5O3 minus, it's both x. So we plug those values into the equilibrium equation to get Ka is equal to x squared over 0.5 minus x, and so we know that x is 0.0083, so from those values we can plug that in as x, so we get 0.0083 squared over 0.5 minus 0.0083, and we can solve from there to get a Ka value of 1.4 times 10 to the negative 4. Because I got part B right, I'm not going to go over that, but basically it's just finding the pH, and so you just use negative log of the Ka value. For C, calculate the pH of solution formed by dissolving 0.09 moles of solid sodium lactate in 250 milliliters of a 0.5 molarity HC3H5O3. So what I did wrong was I didn't know how to set it up, and I also multiplied the wrong numbers. So instead of doing that, I should be taking 0.09 moles of NaC3H5O3 and divided by the volume, which is 0.25 liters, to find the molarity of C3H5O3 minus. So then we can plug that into an icebox with the equation given to us in the first part. And so we have 0.5 molarity for HC3H5O3. Its change is minus x because its coefficient is 1. So we have 0.5 minus x for its equilibrium. For H plus, we have none initially, and so we have x for change, and equilibrium is x. For C3H5O3 minus, we have 0.36 molarity, which we just solved for previously, and so the change is plus x, so we have 0.36 plus x at equilibrium, and so we can plug those into our equilibrium equation to get 1.4 times 10 to negative 4 over our Ka, which we solved previously, is equal to x times 0.36 plus x divided by 0.5 minus x, but for this we can use the shortcut method. So we have x times 0.36 over 0.5 is equal to 1.4 times 10 negative 4, and then you solve that as algebraically to isolate x to get 1.9 times 10 to negative 4 molarity, which is our concentration for H plus. And so we can find the pH by using negative log of the concentration of H plus, and so after we calculate that we get a pH of 3.71. For D, a 100 milliliter sample of 0.10 HCl is added to 100 milliliters of 0.5 molarity 3H5O3 and to calculate the molar concentration of lactate ion in the resulting solution. What I did wrong was that I took the volume and multiplied it by the molarity to find the moles of HC35H5O3 and HCl, or in this case H+, when I actually should be taking the molarity given and dividing it by the thing's volume over the total volume to find the molarity. So I have 0.5 molarity HC3H5O3 times 100 milliliters over 200 milliliters, because that's the total volume, which equals to 0.25 molarity HC3H5O3. I also have 0.10 molarity HCl, and I can multiply that by 100 milliliters, which is how much there is added, over the total volume, which is 200 milliliters, to get 0.5 molarity H+, and then using that, I can plug that into the ice box. So for HC3H5O3, I have 0.25 molarity. For H+, I have 0.05 molarity. And for C3H5O3 minus, I have nothing initially. So as always, the change would be minus x, and plus x, because we use the coefficients. And so for at equilibrium, for HC3H5O3, we have 0.25 minus x, H plus is 0.05 plus x, and C3H5O3 minus is just x. So we can plug in those values into the equilibrium equation to get Ka, which is 1.4 times 10 negative 4, which we solved for previously, is equal to x times 0.05 plus x over 0.25 minus x. But for this case, we can ignore the x, and so we have 0.05x over 0.25, and then we can solve that algebraically to isolate x by multiplying 1.4 times 10 negative 4 by 25 and dividing it by 0.05. And so for x, we get 7 times 10 to the negative 4 molarity, which would be the concentration of the lactate ion C3H5O3 minus.